so it looks like we're not supposed to pick up any homework until at a minimum of next week. So pretty much everything I've assigned will be due next week at some point. Uh, First, any questions about class or assignments or how a school is going to work, things like that. Hello. Hopefully there's less delay. I think I was able to change the settings to where I can see your replies pretty fast. School, it sounds like it's mostly going to be pretty much completely online. I think we're allowed to start assigning things next week, but it sounds like most classes things aren't really going to start until 2 weeks from now. Um, yeah, you may have heard the school is shut down until April 3rd. That's just until they reassess. I forget what state it was, but one state just shut down school for the entire state for the rest of the school year. So just be ready for this possibly being a little bit longer. But I don't have any official word other than April 3rd. Yeah, the 23rd, that's when we were given, we aren't supposed to pick anything up this week, so everything you have, if you look, everything's been pushed back to being due on either the 24th or the take-home test, I think I still put due on the 23rd. Any other questions? No other questions, so mostly about the take-home test was, yeah, I can do take-home test questions. 173 and 174. Yeah, does this one just not have a picture? I think this is one you're talking about. Uh, yeah, so because these don't have pictures, I can't really grade that. Uh, for you, I would say talk to Mr. Lambert. He probably will take that question out also. Any other questions? And for my class, the assignment on College Board closed because I set the due date, but I just recently reopened that. So today it's completely reopened. So if there's any questions you have about the homework on College Board, I can look at that or the test assignment. Uh, some people were able to upload the entire assignment for the take-home test. They were able to take pictures and post it. Some people weren't. They were only able to do 20 at a time. That's why I gave 3 different places you can turn that in. Number 92. Here, I'll be right back. Alright, the bob of a simple pendulum weighs W. A horizontal force is applied on the bob, displacing the string through an angle theta from the vertical. The tension on the string must be. So, again, if someone would put timestamps for the different questions I talk about, that would be really convenient for other people. I need to see about that. I wasn't able to see a way to reopen that. I'll check that in just a second, though. If for whatever reason I can't get it to reopen, I'll just make another one with the exact same questions. But I'll try to do something so I don't have to do that. So give me a second and I'll try to reopen that for you after I do this question. Alright, so we have the pendulum. It's pushed to some angle theta. And we're pushing with a horizontal force. We'll just call this FA, applied force. So let's draw this a little bit bigger. So I have my pendulum here. What am I doing? Actually, let's not draw it like that. Let's just put it on a free body diagram. All right, so we have tension holding it up and over. We have the weight pulling down. The weight is going to be more than the tension because the tension is not holding up the entirety of this. If I let go, it's going to slide down. So I also have this applied horizontal force. Now, what does it say? Is it? Yeah. Good morning. So yeah, it's displace the string an angle of, from the vertical. It doesn't actually say how the applied force is acting, but so we can't really do anything from that, but I am trying to split up this tension force. I know my angle theta here, which means this side is adjacent, this side is opposite. So that means if I do a force resolution diagram, we'll have this tension times adjacent is my vertical. Adjacent is going to be cosine of the angle. I have an applied force this way. And then The horizontal component of tension is the opposite from this given angle. So opposite is going to be sine. So this is going to be tension times sine of the angle. And then we have the weight holding this thing down. Yeah, there's not quite enough information here based on what it sounds like the question was trying to ask. I think it's displaced and then it stays at rest. So I think that's what they're getting at here, actually. So I think they're saying this is displaced and when it gets here it stays at rest. That's not what the question actually says, but otherwise we don't have enough answer to do that. We don't have enough information to do that, which would mean that all of my forces are going to have to balance each other. And that means we would actually have less weight here because the tension would have to cancel out weight and the applied force. So when we see this, tension times cosine of the angle equals weight. And then so we're trying to get tension. So tension would be weight divided by cosine of the angle. I'm looking at the answer key. This is clearly what they were trying to get you to do, but they didn't give us enough information. They should have said something about it's either moving at a constant speed or until it reaches its maximum angle and it stays at rest. But otherwise, yeah, that was actually a poor question. What grammar question? I guess no grammar question. All right, we'll do number 14. Look at 14. I'm going to go try to reopen the assignments of the people who submitted them. So I'm going to be looking at that for just a second while you look at 14. Yeah, I'm just going to end up curving the test because that's about all I can really do. Uh, my wife actually went to get me Jack in the Box this morning. A lot of her clients have canceled, and so she's home later this morning. I don't know if she can hear me talking about her or if she has her headphones in. Um, Nothing has been curved yet, so I still need to go through and curve those. It says here I can unsubmit. I'm just trying to click on the students. It's not letting me. Can you still pull up your quiz even though it's been submitted or not at all? Okay, so you can't open it. Yeah, this website says I should just be able to open it. Assignment report. Here, I'm gonna go to my other computer to try to do this. This computer is being really slow. So, give me a few minutes. It kind of looks like there isn't an option for me to unsubmit that. So I think from now on, you don't need to submit any of these. I can automatically make it submit at the very end. So when you finish this, try to just hold off, don't submit it, and then I can submit it for you. So that would probably be the best thing to do. It seems like I can't do it from this one I do here. The only ones I can unsubmit are their official progress reports, which is pretty obnoxious. All right. So you can pull that up now. I'm sorry if you have to redo some of that. I'll keep working on that after this and see if I can do anything about it. All right, so number 14. All right, ball 1 is dropped from rest at time t equals 0 from a tower of height h as shown. At the same instant, ball 2 is launched upward from the ground with an initial speed v0. If air resistance is negligible, at what time will the two balls pass each other? All right, so when we're looking at this, what's going to be the same for those two objects when they pass each other? All right, so their y position will be the same. Their time will also be the same. I'm going to look at the y position. It's going to be a little bit easier. So we know their initial speeds, but we don't know anything about their final speeds. So if we don't know anything about their final speeds, what equation are we probably going to use? And again, we can use kinematics on this one for all of you who always want to use kinematics on everything. So we can use that second kinematics equation. So our final y position is equal to the initial y position plus the initial y velocity times time plus 1/2 acceleration in the y direction times time squared. All right, so we have the object that's dropped, and then we have the object that's launched. So the dropped object starts at rest. So the final position is going to be the initial position. This one drops from height h, height h, plus the initial velocity is 0. Plus 1/2. Acceleration is going to be g downwards. Again, we're going to use the convention that they give on your formula chart. The acceleration due to gravity is 9.8 meters per second squared for any of you in Lambert's class. So I'm going to call g positive 9.8 meters per second squared, and I'm going to put the negative to say g is downwards. All right, the one that's launched, final position, it launches from the ground, so it starts with a height of 0, but this one is moving when it launches, so that v0 times time. And then it's also experiencing free fall after launching, so it's accelerating downward with negative 9.8 meters per second squared acceleration, time squared. All right, so these are going to be equal to each other. When they're at the same position, they're going to have the same final y position, so I could just set these two equations equal to each other. So that height minus 1/2 acceleration due to gravity times time squared is going to be equal to the initial velocity times time minus 1/2 acceleration due to gravity times time squared. And something really nice falls out of this equation. Yeah, I'm going to intentionally give you something that's just absolutely horrible with kinematics. I'll make it possible, though. Alright, so add those to both sides, so we end up with height, h, is going to be the initial velocity times time. We're trying to find time, I think. Yeah, we're trying to find time. So time is going to be height divided by that initial speed. Yes. But yeah, it's just, if they're trying to find the time whenever they're at the same height, then, well, we're probably trying to solve for their final y position, and we can just set that up. Well, if they have the same height, they have the same position, so I can just set these two equations equal to each other. That's a pretty common type of kinematic type question, when two things pass each other. So you would set their positions equal to each other, or what position are they at if they pass each other at this time, and then you would set their times equal to each other. Alright, so we'll do 88, and then which one was 183? I'll look at that in a second. Alright, 88. Oh, dang it. I tried to change the bitrate of this so the video would stream faster, but it still seems pretty delayed. So I guess we're just stuck with that 15-second delay continuously. Alright, so 88. A ball of mass m is suspended from two strings of unequal length, as shown. The tension T1 and T2 in the strings must satisfy which of the following relations? So this should be pretty fast. Oh, whoa, my key is wrong. Well, we have this, we have this. I can't imagine a way to use kinematics for this one. So this is tension 2, angle 2, angle 1, tension 1. So I could pretty quickly say that tension 2 is bigger because it has to support more of the weight. So we could just leave it at that, but yeah, tension 2 is definitely going to be bigger than tension 1. But let's at least just look at the vertical part of my force resolution diagram, or I guess I can look at both. My vertical right here, so when I'm trying to split up this angle, let's draw a triangle a little bit bigger. So I'm trying to split this up. If my angle is right here, then this side is going to be adjacent, this side is going to be opposite. So adjacent is going to be cosine theta, opposite is going to be sine theta. So each of these I'm going to have tension 2 times cosine angle 2, and I was actually just wrong with what I said. Don't listen to what I said earlier. Tension 1 times cosine angle 1, and then I'm going to have tension 2 times sine angle 2, tension 1 sine angle 1. These have to be equal lengths, and then this is all supporting the weight. So I could get two equations from here. I know tension 1 times sine of angle 1 is equal to tension 2 sine angle 2. And I can also get tension 1 cosine angle 1 is equal to tension 2 cosine, not equal to, plus tension 2 cosine angle 2 is balancing out the weight of this object. Now, I'm going to look at the simpler equation for this one. So let's look at this equation right here. So I know tension 1 sine angle 1 equals tension 2 sine angle 2. I know angle 1 is bigger than angle 2. And since we're dealing with sine, a big angle means a big number, right? So sine of theta 1 is greater than sine theta 2. Right, because sine 0 degrees equals 0, sine 90 degrees equals 1. So we know sine angle 1 is bigger than sine angle 2. Tension 1 times sine angle 1 times is equal to tension 2 sine angle 2. So I could look at this. If this number, sine angle 1, is big and sine angle 2 is small, that means I would have to multiply a small number times a big number, and I would multiply a big number times a small number in order for these to be equal. So that means tension 1 has to be smaller than tension 2. So I would say tension 2 is greater than tension 1. Then yeah, the correct answer on my sheet, they just wrote it wrong. They just wrote the equation, the n=, sign incorrectly. So I think you said 183 next. I just got an email. Let me check that. No, nothing important. So we can do 183 next. Any last questions or confusions over the last one, 88? Ooh, yeah. 183, I'm not going to grade that. That is not a algebra-based physics question. Yeah, we're not going to do 183. Yeah, you can use parallel axis theorem. If you do 183 and do parallel axis theorem and turn that in on a separate document under... Actually, probably just email me would be best. By the way, I'm trying to check my email a lot, so if you ever have questions on email, I'm trying to respond to that pretty much throughout the day. But yeah, I'm not going to grade 183. Any other questions? Either on here or on the homework. 173 and 174, those are the ones without anything. Yeah, ignore 173 and 174. I'm not going to grade those. And if you're a Lambert person, tell him that those don't make sense, and tell him that 183 is parallel axis theorem. Use kinematics. You could use rotational kinematics if you were solving for it experimentally. Oh, this is a fun one. Alright, a box of mass M. Did Lambert put it together by himself. Honestly, when you're throwing a bunch of these together real fast, it's really easy to miss things like that. So, if you did a lab, that would actually be okay. We're still going to do some labs. I've been building a few of them that we're going to do. So we'll probably do a lab with rubber bands for elastic constant next week at some point. Alright, we have a box of mass M pulled along a surface with friction constant mu. The rope pulled at an angle of 30 degrees from the horizontal with a force FR. I can't read that actually. FR, I think, yeah. What is the acceleration of the object, assuming the force is strong enough to set it in motion? So we're going to make a few assumptions. So the force is strong enough to set this box in motion. We're also going to assume this force isn't strong enough to pull the mass off the ground. You could actually build me a transformer. Alright, so first things first. Forces, we should probably draw a free body diagram. We have a force getting pulled this direction. We have the weight down, and let's just be even more certain. That weight needs to be bigger than the vertical component of this so it doesn't fall down. We're going to have a small normal force, right? Because this force is pulling up as well as right. It's that upward force. So because I'm pulling this box up a little bit, the ground, the surface, doesn't have to support as much of the weight. So the weight is supported by the surface and the person pulling up and over. All right, and then does it say anything? What are we actually trying to solve for? What is the acceleration? So because there is an acceleration, it's enough to set it in motion. That means we're going to have a smaller frictional force. All right, so we have our free body diagram. We need to do a force resolution diagram because this force here is at a weird angle. So normal force already perpendicular to the surface, weight already perpendicular to the surface, friction already parallel to the surface. So that just means splitting up this applied force. So we're given the angle theta from the horizontal right here. So our angle theta there. This is FR. Trying to find how much goes right and how much goes up. All right, so we have our adjacent right here. We have our opposite right here. So adjacent is going to be cosine, so that's the applied force times cosine of the angle. This is my opposite, so that's going to be applied force times sine of the angle. So we have cosine to the right. We have sine up. And I know this is a sketch, but still let's try to make sure up 1, down 2. That way we're not accelerating in the y direction. Let's make sure we have the same amount up as we have down, in case they actually didn't have that. So up 1, down 2. So if we have the same up forces as the same down forces, that way we don't accelerate up off the table or down into the ground. All right, so we could get two equations from this. So I know these two forces are not balanced. So that means I have a net force. The net force is mass times acceleration, but the net force is going to be the difference of these two forces. So the applied force times cosine of the angle minus the force of friction is equal to the mass times acceleration. I can also get my equation from these vertical components. So I know normal force up plus that applied force times sine of the angle is equal to the weight, mg. Now this one, normally we care about this because we're trying to get our normal force. Normal force helps us get our frictional force, so let's solve this one for normal force is equal to weight minus that applied force times sine of the angle. All right, so we have this here. We're going to have to get our frictional force somehow. So the magnitude of frictional force is less than or equal to the coefficient of friction times the magnitude of normal force. Now, it says we have, where is it? Assuming the force is strong enough to set it in motion. So this is implying that it's not in motion, but it's about to be in motion. So it's enough for it to slide across the surface. So because this can slide across the surface, there's motion between the two surfaces. We will have an equal sign here. So our frictional force is going to equal the coefficient of friction. And we just solved for our normal force here. Mass times acceleration due to gravity minus that applied force times sine of the angle we pull at. So we can combine these two equations together to get that applied force times cosine of the angle minus, we know our frictional force is that coefficient of friction times mass times acceleration due to gravity minus that applied force times sine of the angle is all equal to mass times acceleration. And there we go. All right, so we're ultimately trying to get acceleration, so we're going to divide our mass over. So we'll get our applied force times cosine of the angle minus the coefficient of friction times mass times acceleration due to gravity minus applied force times sine of the angle divided by mass is equal to acceleration. And what answer choice looks like that? Oh, we actually have angles. That's what's happening. We can actually plug these in. So cosine of 30 degrees is what? And sine of 30 degrees is what? And these are both on the back of your formula chart. So square root of 3 over 2 and 1/2 respectively. So I get the square root of 3 over 2 force applied minus that coefficient of friction. Is still, yeah, they're leaving it in the square root. Coefficient of friction times mass times acceleration due to gravity minus 1/2 applied force divided by mass is equal to acceleration. And so that one looks like B, I think. Yes, B. $124. Just give a second if anyone has any questions. $124 and $189. All right. All right, a disk of mass m slides with negligible friction along a flat surface with velocity v. The disk strikes a wall head-on and bounces back in the opposite direction with a kinetic energy 1/4 of its initial kinetic energy. What is the final velocity of the disk? All right. So it goes and it hits the wall and it bounces back with 1/4 of the kinetic energy. So one way of saying this is my initial kinetic energy is going to be 4 times my final kinetic energy, or I could have written it as my final kinetic energy is 1/4 the initial kinetic energy. All right, I kind of like this because I don't want to deal with fractions. But yeah, I have to multiply my final kinetic energy to get what my initial kinetic energy is. So I have 1/2 mass times the final speed, not final speed, initial speed squared is all equal to 4 times 1/2 mass times that final speed squared. Now both sides have a 1/2 and both sides have a mass, so I can divide those, send those to 1. We're trying to find, what are we trying to find? What is the final velocity of the disk? So we're trying to find the final, actually, speed because we don't have direction. So we're trying to find the final speed of that disk. So let's divide the 4 over. So I have initial speed squared divided by 4 is equal to final speed squared. I can square root both sides. So the final speed is going to be the initial speed divided by 2. Yeah, are there any of the answers negative? Okay, yeah, so it does actually ask velocity. So it bounces back, so this would be the final speed, but the final velocity is negative times that initial speed divided by 2. Yeah, because it bounces back. So let's kind of go a little bit more in order. I'll do 189 to 199. Alright, a 2 kilogram object moves in a circle of radius 4 meters at a constant speed of 3 meters per second. A net force of 4.5 newtons acts on the object. What is the angular momentum of the object with respect to an axis perpendicular to the circle and through the center? Alright, so pretty much every time we're looking at a point mass, we're looking relative to the center. 189. So again, we're trying to get the angular momentum. Wait, I think that's what we're trying to get, right? What is the angular momentum? Yes. So angular momentum is going to be the moment of inertia times angular velocity. But we know angular momentum of a single mass. Now it just said a single mass, so we're going to assume this is a point mass, so it's going to be small compared to the size of the circle. the mass is going to be concentrated compared to the size of the circle. So the moment of inertia of a point mass is mass times radius squared. Again, this is really the only thing you need to know about moment of inertia. It's something mass times radius squared. You might have some number out front. If it's something else with a different number, you'll just be told that until you get to a higher level of physics where you'll be expected to solve for it with integrals. All right, so we have moment of inertia for a point mass. And again, now we have a point mass, so we're going to have to get the speed in terms of angular speed. Well, I know that tangential speed is going to be angular speed times radius, just like the other equations we were able to get, like the distance traveled is going to be the angular distance traveled times radius, or that tangential acceleration is going to be angular acceleration times radius. Equations not given to you that you should probably know. But we're trying to solve for angular speed to put into my equation. So I know angular speed is going to be tangential speed divided by radius. So I can combine these together, put this here, put this here. So angular momentum for a point mass, for a single mass small compared to the rotational motion, is going to be moment of inertia, mass times radius squared. The angular speed is going to be that tangential speed divided by radius. Radius squared divided by radius. We just get mass times speed times radius. And if it's angular momentum, mass times velocity times radius, if you're not just looking for the magnitude. And now we can just put some numbers in. The mass is 2 kilograms, radius 4 meters, speed of 3 meters per second. 2 kilograms moving at 3 meters per second at a radius of 4 meters. 4 times 3 is 12, times 2 is 24. 24 kilograms meters squared per second. Why doesn't force affect angular momentum? Yeah, why is this talking about a net force? It doesn't give us enough information to use that net force to do anything. Yeah, net force over how much time and what direction. Oh, okay, yeah. That's right. Good point. So it's there we go, constant speed. So because we have a constant speed, that means we're going in a circle. Where did you go? That net force is just that centripetal force. Yeah. So we're going around in a circle like this. So we have a centripetal force is 4.5 newtons. And we have a constant velocity. So because we have a constant velocity, we have a centripetal force, but that means my tangential acceleration is 0 meters per second squared, which is how I can maintain a constant speed. I shouldn't write constant velocity, constant speed. Because our velocity is constantly changing. Because we have a changing direction, so we have a changing velocity. And if we have a changing velocity, we have to have a net force. All right, so wait, the other one was 199. The radius of a collapsing spinning star, assumed to be a uniform sphere, decreases to 1/16 of its initial value. What is the ratio of the final rotational kinetic energy to the initial kinetic energy? All right, so we're trying to find a ratio. The final kinetic energy to the initial rotational kinetic energy. What changes? Oh yeah, the radius. Okay, yeah, this is going to change. Never mind. All right, so rotational kinetic energy. So I have 1/2 moment of inertia initial angular speed divided by 1/2 final rotational inertia final angular speed. So 1/2 will go to 1, divide out. So we have a sphere. Stars are close enough to being a solid sphere. Sphere. I need to actually look this up. I think it's 2/5 mr squared. Let me go check that. I could be wrong. Yeah, 2/5 mr squared for a solid sphere. We'll assume the star is solid. All right, so I can put this in here. So this is going to be equal to 2/5 mass times radius squared divided by, this is going to be the initial, divided by 2/5 mass times radius final squared. Yeah, we are going to have to do this. All right, so the speed is going to be angular speed times radius, that tangential speed. So angular speed is going to be tangential speed divided by radius. Actually, let's not do that. So energy is not going to be conserved, but there's no net external torque. The net torque is 0 Newton meters, which means that the angular momentum is conserved. So the initial angular momentum equals the final angular momentum. So angular momentum is moment of inertia times angular speed. Initial is moment of inertia final, angular velocity final actually. Yeah, how should we go about this? Guess we can just use this. So moment of inertia initial is that 2/5 mass mass times radius squared. Initial angular speed is equal to 2/5 mr squared final angular velocity. Divide out 2/5. It said nothing about the mass changing. I can't imagine how I'd get any further away than it from anyone. This is initial, final. So I know the final radius is going to be 1/16 of the initial radius. Or I could write this as 16 times that final radius is equal to the initial radius. Yeah, we'll do 156 next. So initial radius squared times the initial angular speed is going to be the 16. Actually, I should have written it that way. 16 times the initial radius squared is equal to final radius squared times final angular speed. 16 squared, radius initial squared. You can divide out. This is final. You can divide that out. So 16 squared times the initial angular speed is equal to the final angular speed. So this equation down here, we're looking at initial radius squared times the initial angular speed divided by final radius squared times the final angular speed. There's probably a faster way through all of this, but we'll just do it this way. So then we have 16 radius final squared all divided by radius final squared. The final angular speed is 16 squared initial angular speed, and then we'll just leave this as initial angular speed, divide that by that, radius final squared divided by radius squared, 16 squared divided by 16 squared. Does this just all cancel out, or did I do something stupid along the way? Something went wrong here. Oh, okay, I see what I did. Yeah, it's 16 squared here for the, no, that's not it. It should just be 16 squared, yes. But I did something silly along the way. Yeah, if you see what I did wrong, tell me. Angular, oh, yep, there it is. All right, so this is squared, squared, so 16 squared squared divided by 16 to the 4th. So I get 1 over 16 squared. So final to initial. And this is saying Oh, I did opposite. They wanted initial final rotational kinetic energy to the initial. I kind of dislike how they worded that answer. But yeah, the ratio between them is going to be 16 squared. I mean, the final would be 1/16 squared of the original, or the original would be 16 squared times the final. So 156, 176. No, questions are fine. I can honestly do this maybe until about 12. I think we're supposed to give 2 hours of tutoring each day anyways. 156, 176. Besides, everyone doesn't have to look at this, so... Alright, a small mass released from rest at a very great distance from a larger stationary mass. Which of the following graphs best represents the gravitational potential energy U of the system of the two masses as a function of time t? So, very great distance. What is that saying we can't use? Yeah, so very great distance. We can't just use mgh for gravitational potential energy. Very great distance, I can't use this. This equation works well near the surface of the Earth. Of Earth or any other object like Mars or anything else. It doesn't just have to be Earth. So yeah, we can't use this. That means we're stuck using our other gravitational potential energy equation. So gravitational potential energy is negative gravitational constant, mass of the object, mass of the planet, and all divided by radius. Now when we're graphing at this, it might be useful to kind of look at this. So we have gravitational potential energy is on the y-axis, so gravitational potential energy is going to be some constant, negative gmm. I really don't care that much about that. I just care about this 1 over r. So negative means below the x-axis, because I'm going to have a negative gravitational potential energy. And then which one of these is a 1 over r relationship? We have 2 below the x-axis, or 3, E, B, and D. B doesn't look right. That's linear. That should be just x, not 1 over x or 1 over r. So, D or E. And when in doubt, just put it in your calculator. Negative 1 divided by x, not minus, divided by graph. I don't know if you can see that well. But isn't the x-axis time, not radius? Okay, yeah, it is released from rest. Okay, good point. Yeah, that is time. Released from a great distance. So as it gets closer and closer, all right, that's a good point. So if it gets closer, so as time goes up, we're seeing the radius go up. So as time goes up, we see our radius go up. So as radius goes up, our gravitational potential energy gets more negative. Right, because as we get a bigger and bigger number here, we get a smaller and smaller number. Actually, it gets less negative. What am I saying? But it's negative, and then as this gets, time goes up. No, radius goes down. That's what I was trying to say. Yeah, time goes up, radius gets smaller, we drift closer to the planet, we fall towards the planet. Radius goes down, gravitational potential energy gets more negative. So as time goes up, smaller and smaller radius as we fall closer, more and more negative gravitational potential energy, because as I get a smaller and smaller radius, I have a bigger number, but a bigger negative number. So which one of these has a value that's getting bigger and negative continuously? Yeah. Yeah, D. DDoS. Yeah, don't DDoS me. Wait, what was the next one? 176. Yeah, 176. The district has not said anything about extending the school year, but the principal kind of said what I've suspected a little bit. Because teachers aren't on a break this week, and we have a very specific contract for a set number of days, if they extended the school year, they would have to pay us extra, and I don't think they're going to do that, so I kind of suspect, just as Ariola expects, we're probably not going to extend the school year, but we're still waiting for direction from the state. So that's not going to be a question that even the school district can answer. That's going to be a question that the state has to answer. So hopefully they'll tell us soon. My suspicion is no, not extended school year, and if it is, maybe a week or two at most, but we'll see. And again, don't take anything I say as absolute truth. I could be absolutely wrong on all of this. So if you hear something I say and then you hear something the district or principal says, listen to them. They have better advice than I do. They know a lot more than I do. Alright, so 176. We have a cylinder. And we have a rope wrapped around the cylinder and hanging down the edge with a mass M. The cylinder has a mass of capital M. Wait. Oh, but they actually give us some masses. All right. So first things first, we can look at our equation. I need to pull this up. we can look at our equation for angular acceleration of this object. So we have our Newton's second law in rotation is that angular acceleration is our net torque divided by moment of inertia. Now, torque is going to be radius times force times sine of the angle between radius and force, which for this one is just going to be 90 degrees. Anytime you have something hanging off the edge of a cylinder, it's always going to be 90 degrees. But the easiest thing to mess up on this, that almost everyone messed up on the test, is it's not the mass directly pulling on this. What directly pulls on this is the tension divided by moment of inertia, so 1/2. Let's be careful here. It's mass of the cylinder times radius squared. Sine 90 goes to 1. 1 divided by 1/2 is 2. Angular acceleration is going to be 2 times the force of tension divided by mass, and then radius divided by radius squared just is 1 divided by the radius. Alright, we can do 118 after this. Alright, so that's my angular acceleration. Now, we're trying to get the acceleration of the... find the acceleration of that hanging mass. Now, the key word here is this does not slip. If this mass doesn't slip, that means the acceleration of the cylinder, the tangential acceleration of the cylinder, will exactly equal the tangential acceleration, or the downward acceleration of that mass. If the string slips, if there's any motion between the two objects, then those will not perfectly balance. But because the string is perfectly attached to this, these have to go the same speed and have the same acceleration. So all that is me pretty much just saying I can use that tangential acceleration is angular acceleration times radius, or angular acceleration is going to be that tangential acceleration divided by radius, and put that here. So acceleration divided by radius is going to be 2 times tension divided by mass times radius. I can multiply both sides by r, and that just ends up being acceleration is 2 times tension divided by mass. All right, now we need to look at our hanging mass. So for our hanging mass, we're going to need to draw a free body diagram. Hanging mass. We're going to see that this has a smaller force up than down. This has to be the case. Otherwise, if we release this and I don't have a bigger force down than up, it's just going to sit there. It also has to be the case if this thing doesn't have friction and there's only a force applied to one side, this thing is going to turn and this is going to fall. So as long as there's no friction, this mass is always going to fall if there's nothing stopping this from turning. So that means we're going to be using our net force equation. So net force equals mass times acceleration. Net force, big minus small, so mg minus tension equals mass times acceleration. We're ultimately trying to find tension here, so I can substitute that into this equation. So I'll add tension, subtract ma, so mass times acceleration of gravity minus mass times acceleration is equal to tension. And I'm being very deliberate. This is lowercase m because this is the hanging mass. This one was capital M because it's the mass of the pulley. And I can put these both in right here so that acceleration is going to be 2 times the weight of the hanging mass minus 2 times mass times acceleration of the hanging mass divided by the mass of this object. I can put in some values here. So 2, the hanging mass is, what's the hanging mass? 1 kilogram. 2 times 1 times, they're just using G is 10 on here. A lot of times on the AP test, you're allowed to just use G equals 10. All right, minus 2 times 1, I don't know this acceleration, all divided by the cylinder has a mass of 6. Multiply this over, so we end up with 6A is equal to 2 times 1 times 10 is equal to 20, minus 2 times A minus 2A. I can add this over, so I get 8A is equal to 20, or A is equal to 28ths, which 28ths, what is that, 2.5 I think? Is 2.5. There goes my calculator. Is that the answer? Let's see, I don't actually have this up. 176 is 2.5 meters per second squared, yes. This calculator is good. It's probably as old as many of you are. I got it in like 2003. It survived being dropped. It survived being so completely waterlogged that it glitched out for a while, and I dried it out. This thing seems pretty indestructible. No, it's a TI-83. Please don't break my calculator. It's as old as some of you are. Yeah, younger by a year. It's about to be older than some of my students. It's actually pretty comparable to the TI-84 in terms of actual features. The TI-84 is just kind of a reskin with a slightly different operating system. Let's see, so 75, there was one before this though, right? 118, so yeah, I'll do 118 then 75. Can it run Doom? Probably not. You can run Doom on some of the Inspires, right? Or some people were able to get some emulators on there. I don't think it runs them well, but it's interesting to say the least. Alright, 118. I know the TI-83 is some like ridiculous amount of times more powerful than the computers that got Apollo to the moon. Just crazy to think about. Alright, 118. When an object is moved from rest at point A to rest at point B in a gravitational field, the net work done by the field depends on the mass of the object and... Alright, so this is a good question. This is getting to the difference between a conservative force and a non-conservative force. So, a conservative force does not care about the path that I take to get there. It only cares about the endpoint. Only cares about beginning and end. Beginning and end. I dropped it in there. Whatever. Non-conservative force depends on the path. So, a conservative force doesn't care about how I get there. It only cares about where I start, where I end. Forces like this are going to be like our force of gravity. We haven't gotten there yet. Another conservative force is going to be the electric force. Similar to displacement versus distance, yes. So a conservative force, you're going to be using displacements. A non-conservative force, you're going to be using distances. A non-conservative force, this is going to be any type of friction or air resistance, but air resistance is just a type of friction. So a conservative force, so force of gravity is a conservative force. It just cares about where I start, where I end. This is talking about the net work done. So that's kind of how it's written on your equation. Net work is going to be change in energy. But on our equation sheet, we have our change in gravitational potential energy is equal to mass times acceleration due to gravity times change in height. So again, this is only caring about deltas, delta x, delta h, where this is talking about the entire distance. So when I'm looking at this, let's look at which one is correct. The net work done depends on the mass of the object, the positions. It doesn't really care about the total position of this, right? It only cares about the change in height. It doesn't care about the path. So if it doesn't care about the path taken, like friction would, then it can't do C either. D, the velocity of the object as it moves between A and B, that doesn't matter as long as it gets from A to B. Nature of the external force, that doesn't matter. So I guess they are getting at A, even though they said just positions of A and B. I would write that a little bit more precisely as the heights of A and B. But yeah, that should be A. Yeah, I kind of dislike the wording on that, but whatever. 118, yeah, A. All right, 75. All right, so 75 is talking about inertia. What is inertia related to? So inertia is pretty much just talking about mass. More mass, more inertia. I have a lot of mass, so I have a lot of inertia. It's hard to start me moving or to stop me moving. And then a smaller object, like my cat, has a small inertia. I can easily make him move when he's laying on my side of the bed. I can just shove him out of the way. But he can't shove me out of the way because I have a lot of inertia. And then, so yeah, you're just picking the one with the most mass. Any other questions? $132. And I'm probably going to end this stream at around 12 so it doesn't go too long. So just be thinking of any last questions that you have, kind of quick ones. And I'll probably come back on Friday morning at around the same time. Just for questions on this and the homework that I posted. And I might have to like pull out my really long HDMI cable and just connect it in here because I can't stand this laptop very much longer. It is pretty garbage. All right, an object is dropped. Wait, that's not one. Yeah, 132. An object is dropped from rest from a certain height. Air resistance is negligible. After falling a distance d, the object's kinetic energy is proportional to which of the following? I would show you my gaming setup, but my room is an absolute mess. And it's even worse because I'm pulling out a lot of my own things to build lab equipment. And yeah, it's just a mess in there, and I don't want you to see that. Clarify turning in the take-home test on Classroom. So the take-home test, some people were having issues putting all of the attachments into a single assignment on Google Classroom. One person was able to do it, but a lot of people weren't. So that's why I set it up to where you could do pages 1 through 20, 21 through 40, and 41 through the end. If it lets you put them all on one, then that's okay. But if it doesn't, then you can change that. I set my specs the other day. It's a GTX 1070 i7 7700K, 16 gigabytes of DDR4 RAM, 2400 hertz, 1 terabyte Samsung Pro solid state hard drive. What else? I mean, that's most of the things I care about. I am not going to assign any more new work this week. So no more new work this week. All right, so 132, object dropped from rest at a certain height. Air resistance is negligible. After falling a distance d, the object's kinetic energy is proportional to which of the following? All right, so we're trying to relate this to kinetic energy, so a good thing would probably be to write the kinetic energy formula. Kinetic energy is 1/2 mass times that final, or that speed square. I don't have to put final. Now, I'm trying to relate this to distance d, so all of you people who really love kinematics way too much, we conveniently have an equation that's written in terms of speed squared and distances. That final speed squared is equal to the initial speed squared plus 2 times that acceleration times final minus initial y position. Now this thing is dropped, correct? Object is dropped from rest. So this is 0. And I'm just going to write this as delta y. We could even just put distance, so that final speed squared is going to be 2 times acceleration times that delta y. And I could put this in here. I could just put this equation right here. So kinetic energy would be 1/2 mass times 2 times the acceleration times change in y position. Yeah, so we should see kinetic energy is just directly proportional to distance. So which answer is that? That should just be D. Yeah, so it's directly proportional because this is like my distance to the first power, kinetic energy to the first power. So it's just, yeah, it is just mgh. Yeah, we just pretty much derived mgh. I didn't see that. So yeah, that's about the time that I had set aside today to do this. We'll have 170, 171. Let me see those real fast. I'll do this again Friday morning. So if you still have questions Friday morning, I can answer those. Oh yeah, 170 and 171, those are the two that... Oh yeah, these are these two. Solid cylinder, mass M, radius R, string wound around it. I can, but I won't. Solid cylinder, mass M, radius R, string around it, person holding the string vertically upward. Okay, yeah. This is pretty much just a yo-yo, right? Cylinder suspended in midair for a brief time. Its center of mass does not move. The tension of the string is T, and the rotational inertia of the cylinder is 1/2 mr squared. For a brief time interval, delta T. That moment when it doesn't move, it should just be 0, right? Yeah. So that brief time interval, it says there, it does not move. So tension string T, rotational inertia, pulls vertically upward. Oh, okay, yeah, I see what's happening. So not quite like a yo-yo. Wait, that's 171, right? So yeah, it's pulled up, not quite like a yo-yo, but because it's pulled up and it's just sitting there, so it stays at rest. Give you emotional support and motivation. The emotional support, it'll be, okay, this virus doesn't affect young people. Motivation, if we all do our part and we all quarantine and we all wash our hands and we all take care of this, it's not going to spread as bad and we can get back to normal. So, I don't even know where my cat ran off to. I mean, just do your best. Just try to stay calm. Like, you're going to be safe. Cat. Just let me finish this one. So this one is saying it's staying at rest. So that means the net force is 0 newtons. And then 171 wants to get the linear acceleration of the person's hand during that time interval. Use your hand. Yeah, so normally when I drop this yo-yo, the yo-yo is going to want to roll down like this, right? So it wants to roll like this. But because I'm accelerating up, it's just sitting there in place. So I'm accelerating my hand upward so it stays there instead of falling down and sliding, all right? I'll show you the cat at the very end. We'll see the cat. So yeah, so because this situation is saying the person accelerates their hand upward, they accelerate their hand upward in a way where the center of mass stays at rest. The thing is still spinning, but its center of mass is not falling down, so the cat's name is Mew. I feel like I've said this before. 171 is the kind of harder part. It might be, actually, let me see. Let's just do this. It might not be as bad. Actually, no, it is going to be annoying. So here it's trying to say what's the upward force on the object. So I could draw a free body diagram. So I have tension up, force of gravity down. Now, if our net force is 0, actually, yeah, that is nice. I know my tension is going to equal the weight in order for my net force to be 0. So that's just going to equal mg. But we're trying to find the acceleration of the hand. So this is going to be accelerating. This is going to get faster and faster as I pull on it. Just the center of mass isn't moving. So I still have an angular acceleration here. My hand is accelerating this way, but this center of mass is not accelerating down, so these are balanced in this specific case. Mutant. All right, so I know angular acceleration is going to be net torque divided by moment of inertia. So torque providing this, the tension is the thing causing the torque, so radius times force of tension. I'm going to be a bit lazy because this is 90 degrees and ignore the sine theta. All right, moment of inertia, 1/2 mr squared. I know angular acceleration, that tangential acceleration is angular acceleration times radius. So angular acceleration is tangential acceleration divided by radius. That is the running joke that if we get another cat, we have to name it Mewtwo. I can multiply radius over to get that radius squared, and then radius squared divided by radius squared just goes to 1. Divided by 1/2, same as multiplying by 2. All right, and then we know the tension is equal to the weight. For this specific case, the tension is equal to the weight in such a way where the thing does not accelerate downward. So I have 2 mg divided by the mass. And so we'll see our acceleration of the hand upward is 2 times the acceleration due to gravity. You're welcome. And then, yeah, we'll do this again Friday about the same time from about 10 to noon. So show up with questions on that. If you got locked out of the College Board assignment, I'm sorry. I really can't find a way to unlock it. I've been trying for a while. I don't think I can with this one. I think it's only the progress reports you can unlock back up. So from now on, any assignments I give on College Board, just don't submit it. When you're done, I can just submit everyone automatically. So just don't ever submit anything on the College Board website. I can take care of that on my end. Once it's due, I'll just submit it all and grade it from there. So yeah, there's that. If you did submit it and you need more time, unfortunately, it looks like you just kind of have to do that again. Hopefully it's not too much effort. I'm really sorry about that. But yeah, just show up here Friday with questions about the take-home test if you still have a few, or if you have questions about the homework on AP Classwork. Again, everything has been pushed back to being due next week. Just follow Google Classroom. I'm trying to be really on top of that. And then, yeah, I'll show you my cat. If you have any other questions, just think of them right now. Where is he? He Like, really likes his chin scratched. Just the cat. I'll have the cat do the tutorial next time. I did a face reveal last time. I guess if you didn't see it, the haircut. Any other questions about more procedural things, like what's happening and when? Man, this bitrate is kind of low. I was trying to change the bitrate. My social security number 123456789. Grades are going to be done. I have not heard, there is no district information yet about grading cycles when they're going to end. I need to go through and just curve exams and quizzes you've already done. So I'm probably going to do that, but we'll get guidance on that hopefully by the end of this week. So I don't know what's happening with the 6 weeks. Yeah. How often do I game? I don't know, usually each day if I have time. Even if it's just for like an hour. I'm just going to curve the test, so I need to curve that test. I'm gonna this 6 weeks, because it's so crazy. I'm gonna try to make sure that as long as you're keeping up on the work on here, that your grade will be okay. I don't want to crush you based on how everything has changed. But yeah, we'll see. I still haven't fully decided how we're doing tests and quizzes. That will be interesting. Any other questions? Well, if there's no other questions, I'm going to end the stream. Just again, I am checking my email a lot more. If you email me, I'll try to actually respond to it. Like a shout out to who's here. Tam, shout out to Daniel, shout out to Steven. James is on here. I don't know who Bob is. Is that Tan? I think someone said that was Tan yesterday. Samir, Nemesis, Lily. Who else? Is anyone else on here? Evelyn, Benjamin, even though you're not in my class, Jocelyn, Camille. I think that's everyone. All right. Made it honest. All right, everyone. Have a good day. I'll be here Friday again at 10. If you have more questions about the take-home test or about the homework, and just email me if you have anything. Post something on Google Classroom. Work with other people. It'll be best if you email me about things that you've asked other people first. That way you can ask me and then you get an answer and then you can spread the information that way. Will probably be one of the better ways to do this. Other than that, everyone, have a good day.